My name is Julia Matevosyan. I'm a chief engineer at Energy Systems Integration Group. I want to welcome you all to 2023 ESIG monthly webinar series and give you a little bit of background on ESIG. For those of you who are not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. ESIG also serves in a leadership role in Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze rapid clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 out of 5 pillars, which deals with research agenda for system operators. For more information on GPST, you can go to www.globalpst.org. We are currently busy in preparation for our meteorology and market design for grid services workshop, which will be held in June 13th through June 15th in Denver, Colorado. This regular workshops this year, we'll also be hosting a simultaneous event, long-term load forecasting workshop. Further information on the workshops is available at our website at www.esig.energy under events. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you are new to ESIG and you like what you hear, I strongly encourage you to follow up with us, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task force. You can find more information about us on www.esig.energy, as well as LinkedIn, Facebook, Twitter, and YouTube. Okay, so now a few logistical matters before we get started. First of all, the phones will be muted for the duration of the webinar to avoid any unnecessary distractions. For the Q&A, as usual, we are using Slido platform. So to ask your questions, please go to slido.com and enter ESIG18 as an event code. The instructions are also at the bottom of the screen right now. You will see a thumbs up button next to the questions, so you can cast your vote and help prioritize questions submitted. We plan to save 10-15 minutes for Q&A at the end and then wrap up at the top of the hour. An email with a link will be provided once the video has been posted, and we also plan to provide short responses to all unanswered questions. So please don't be afraid to ask your questions on Slido. The slides for the webinar will also be posted on ESIG website. Okay, so today's topic will be electromagnetic transient model intake and quality assurance. Continuing industry need for EMT analysis has prompted NERC and others to recommend planning groups require EMT models for all generator interconnections going forward. So this webinar will cover background and drivers behind these recommendations, basic components of EMT modeling requirements, what is involved in ensuring submitted models are appropriate and useful, and challenges involved in implementing such requirements, including schedule impacts, human resource constraints, and acquisition of new skills. So to present this webinar, I would like to welcome Andrew Isaacs. Andrew is a Vice-President of Electranix, where he has been since 2003. He specializes in renewable interconnections, weak grid, SSR, SSCI issues, large-scale EMT system modeling. Additional current efforts include specification and support for FACTS, training for utility planners, strategic consulting, and study team leadership. Andrew obtained his Master of Science from University of Manitoba, Canada. So this time I actually didn't go on LinkedIn to check how many common connections we have with Andrew, because we work in multiple industry forums, and I have a pleasure and honor to welcome him here today, and very excited to hear what he has to say. So just a short reminder, once again, use Slido at slido.com and the event code ESIG18 to ask your questions. And without any further ado, let's go ahead and get started. Andrew, you can take it over.
Thanks, Julia. Can you hear me?
Yes.
And you can see my my screen now, I hope?
Yes.
Okay. Welcome, everybody. Thanks for joining. Seeing quite a few folks on the line. Presentation today, I hope it won't take too long. It's not going to be anything really groundbreaking today. I think you know, a lot of you have been exposed to EMT already and have some idea of what we're talking about, and maybe even have some detailed idea of what needs to be done when you're bringing in models and testing them for EMT studies. Like Julia said, this is something that's sort of been recommended strongly, and we'll go over some of those recommendations. But yeah, so I'm not probably not going to blow your minds today. We're just going to go through some of the basics, talk about why we do this, and then I'll show you some examples of folks who are doing this, and then we'll wrap up with some questions. So I'm going to first introduce myself. And my name is Andrew, like Julia said. I'll introduce my company, actually, and really just as an excuse to introduce my province. So we're a Canadian company. We're based in Manitoba, in Canada. So you might look at some of these pictures and notice that they all are in some way attached to the province where I live. We're located, you know, just above Minnesota, North Dakota. There you can see the little red star. I'm going to also test out my little whiteboard. If I draw on here, I think you should be able to see that. All right. And we've got beautiful northern lights. We've got lots of polar bears, although not in my city. You might know a man named Bill Mason. If you've ever tried to paddle a canoe, I highly recommend you check out these famous videos from this famous Canadian and Manitoban. We're also the home base for RTDS and PSCAD, which are some of the most sort of widely used EMT tools currently in the world. There's lots of others, but and our company has the honor of having as its founders the original sort of the originator of these tools, Dennis Woodford and Garth Irwin. So that's us. We work for all sorts of folks. We work for developers and utilities and geos and OEMs, research bodies, etc. So this is where I live. So that's enough about me. What are we talking about with EMT? So this will start really basic. What is EMT? I think, you know, most of you are aware. Power flow and transient stability programs or phasor domain programs iteratively solve systems of equations in the phasor domain. So 60 hertz RMS quantities is what you get out. So this bottom trace down here is what you would see from a phasor domain tool. Electromagnetic transients are different. Now we can see all three phases solved in the time domain. So we've solved a full system of differential equations in the time domain. So you get every individual phase. If you apply a single line to ground fault, you see that phase go low and the other phases wiggle around, go high, and then it'll clear on zero crossing, and you know, you'll get current zero crossing, and you'll get what the actual power system looks like. So that gives us a lot of extra ability to look at different frequencies or phenomena at different frequencies. We can look at unbalanced faults and harmonics and transients and all those fun things. So what has it been used for? You know, for the past decades, we've been using EMT for lightning, for TOV studies, installation coordination, all those special studies that require really fast looks at transient behavior, switching, energization, harmonics, subsynchronous resonance phenomena, because you need to be able to look at, you know, non-60 hertz quantities in the subsynchronous range. And then control design and analysis was one of the original applications for the PSCAD tool. And for other EMT tools, I shouldn't, PSCAD is kind of our tool of choice, but there are competing products that do the same thing. So what is EMT now used for? Of course, in the last, you know, 2 decades, I would say, and accelerating all through that period, we have weak system interconnections, very high renewable penetration, lots of interconnections of renewables. Other SSO phenomena have become important, you know, control interactions. Fault ride-through evaluation, we'll look a little bit at why that is done using EMT, black start, and some fancy protection analysis. So EMT is sort of all over the place now, and I'd be surprised if you haven't encountered it in one way or another. What's inside an EMT IBR model? So this is going to be kind of the focus of the talk today, as we're talking about IBR models. And then how, before we talk about how we bring them in and check them, we sort of have to understand what's inside, what are we looking for. So inside an EMT model, we have detailed protection algorithms. So that's the everything from individual phase quantity. We can protect based on individual phase quantities. We can implement sophisticated protection and measurement algorithms that are actually in the equipment that can cause the plant to trip. Modern models have software inside that match the specific firmware code that's in the equipment. So there's a DLL standard that you may have heard of, CGRE, Joint CGRE and IEEE standard, or under development, I suppose. That's been quite successful, and many OEMs have implemented this and built their models this way. There's going to be some representation of an energy source. Now, recently, this has been identified as something that's maybe too simple in some ways. Might be as simple as a DC, source, an infinite source, but hopefully might include some more dynamic elements in there, a machine, a PV panel, DC to DC converters, etc. There's going to be some kind of representation of the electrical system, right? We have a bit of the inverter unit itself. Going to have a switching bridge, filter systems, transformers, breakers. And then once you go out to the plant model, you'll either have an aggregate system, which is usually the case for planning type models where you have some aggregation of the collector system and the GSUs, generators, station transformers, anything else that's in the system in the balance of plant that would sort of impact dynamic performance at a transmission level. You may also have, in some special cases, some very detailed, non-aggregated models. Why are we asking for EMT? And the basic answer is, and this is important, I think, to just reflect on, because if this is wrong, we're spinning up a lot of effort and a lot of money and a lot of time for no reason, right? So I think it's important to keep in your mind why we're doing it. And it also helps you reflect sometimes down the road when you get into the muck of it, whether or not, what you're doing right now is important or not, right? Whether it's something that you should take a shortcut on or not do at all. So why do we need it? It's simply to get extra accuracy in our studies to design our grid reliably. So there are some things in our conventional phasor domain tools we just can't see properly. If you look at a subsynchronous control interaction, we just can't see that in a 60 hertz or 50 hertz tool. And inverter-based resources in particular are starting to make us, they're not starting to, they have been making it even more challenging to predict some of these outcomes. And I want to note that you don't always need it. This is something that that fills a gap. When you do need it, we need to be ready to use it. We need to have the expertise and the models. But generally, it's a supplemental tool. It's another weapon in your arsenal of tools to evaluate reliability. We're also seeing events in the power system that are reinforcing that need. We see large chunks of generation tripping off that is impossible to predict. We see subsynchronous control interaction events which show that we're not able to study this without EMT studies. And the other thing I will note is that in the course of the work that we do, every day we're doing these EMT studies, we catch these issues. We catch ride-through issues and interaction issues and oscillation issues instabilities, etc., before they go into service. And this is, you know, for me anyway, and for us living this EMT life every day, it's sort of validated the need to do it. I would just add a little more weight to that. Recent times, and actually this, you can find recommendations like this from NERC going back quite a long way, you know, 5 years at least and more. I think 2017 is probably no longer available because NERC takes them off after a while, but this is a recent one that says EMT models should be required for all newly connecting BPS connected inverter-based resources. Now, this isn't saying you must do a study every time, but it is saying you need to collect the models, because once the you know, the interconnection has happened, it can be very difficult to go back and get those models. If you look at the recently published IEEE standard 2800, which is interconnection for IBRs, it also has in the normative text, the chapter 10, that upon request from the transmission operator, the IBR owner will provide an EMT model. And then further in the Annex G, where they talk about a little bit more in more detail of what those should look like, it says that the TS owner should specify requirements for those inverter-based resources. I'm sorry, I had a slide behind there. To provide EMT models in situations where an EMT study might be needed. So back here, I realize so this is our NERC recommendation here, and IEEE 2800 text, and then Annex G of that 2800 standard says that the TS owner should specify requirements for inverter-based resources to provide EMT models. So, okay, so if we need an EMT model, whether you agree or not, you've decided that you need it. You've decided to get the models. What is inside here that is so special? And I've drawn a very, very simple representation of the controls of an EMT inverter, and the reason for this is really to pinpoint a few pieces that are generally missing from a higher order, I don't know if you'd call it a higher order, a simpler model. So, you know, talking about dynamic models, if we're looking at EMT or phasor domain models, transient stability models, you're going to see common things. You see a power reference, voltage reference, measurements going in. You'll see a power plant controller. Wonder if I can draw with a highlighter. I have a different color here. Sure, here. Okay, so, you know, you've got your power plant controller. Then you have, we won't worry about VDC, VAC references, but you basically are going to be controlling active and reactive power from this device. And you'll have some outer loop controller, right? This is your voltage controller, for example. In an EMT model, because of the high bandwidth of the model, it's running at a much faster simulation time step, and the nature of the solution engine, you're able to look at a lot more detail. So now you can say, okay, so you ordered an active power. You can compare the currents measured right at the inverter terminals and control those currents very tightly to give you the internal voltage reference that you want. So now we're on this, you know, this path here, so that you get the currents out of the IGBTs. You know, you're going to go through to firing controls and actually fire some IGBTs in your model, or maybe you have an average source representation. But in order to do that, you need to have a phase lock loop down here coming in, and that's going to also go to your firing controls. And you also have on the other axis, you will have some kind of a current, again, if you're using a DQ reference frame, you'll have a current comparison at the terminals, that's going to be controlling the Q-axis voltage, or the voltages, so that at the end of the day, when you're generating a voltage source with your IGBT bridge, you're going to produce the active and reactive power that you want. So the piece that's important here is, in many cases, for weak systems, and for something like fault recovery, where you're having very fast changes in system angle, your voltage might go to 0 and then might pop back up at a different angle. You have a phase lock loop, which is a controller that's moving very quickly and trying to resynchronize with the system angle. And you also have these fast current control loops that are trying to maintain the correct currents at the inverter terminals through the IGBT bridge, through the converter. These all have to be very quick and very accurate, and you'll find these are imperfect in any any converter. These are implemented a little differently, and are implemented maybe better or worse, may respond slightly differently to different types of phase angle changes, different types of faults, etc. And the way that they respond and the way that they are integrated with something like a protection, these fast protection algorithms, which can be quite sophisticated actually. They're looking at moving averages, and they're looking at vector representations drawn out of non-60 hertz or transient or messy signals to try and pick out peak, max voltages and things like that. These things are proprietary and specific. These phase lock loops are proprietary and specific. These are actually the secret sauce of a lot of these inverter manufacturers. They will never tell you how they work, but the way that they work will determine whether or not finally you'll have protection operation either in the controls or off to the breakers and trip the plant. So all of this excitement happens in here after a fault clears, for example. So when you have fast events happening in the system, or you have a moment when the converter needs to respond very quickly, or respond to a very severe event in the system, these guys all come into play. And that's why we're looking for an EMT model when we're trying to understand exactly how a plant responds to a fault. What you see in an EMT control model, if you get one, is not going to look like that. It's going to be, black boxes, right? They're not going to show you what's in there. You're just going to see this like a binary set of files for a power plant controller and for the inverter control. So you'll have some user control, you have some measurement coming in. You still will see an electrical representation often of the converter. So you have your firing pulses coming out, you have breakers outside, and so on. You might be able to see this communication, but that's all you'll see. Really briefly, I know this is a dense slide, but really briefly, I wanted to just mention what's in the system model, because we've been talking up till now only about the IBR plant model and mostly about the actual unit level. But in the system model, we have a lot of stuff as well. We've got, if you want to do a study eventually, you're going to put in the transmission lines and cables. So that can be traveling wave models, frequency dependent models. You might have detailed series capacitor models with arresters and bypass breakers and everything. You might have shunt capacitors in the system with different controls. You have to have some sort of equivalent boundary representation. So on the right here, I've shown, an example system model where you have all of the lines and generators and transformers. But you also will have to have at the boundaries of that, since you've had to reduce your system model size, you'll have to have a boundary equivalent of some kind. That equivalent can also be sophisticated. It can be multi-port, might also be frequency dependent, or you might even have, really advanced co-simulation or hybrid dynamic models in your boundary equivalent. Transformers have saturation, remanence effects, fancy core and winding configurations. and you might have detailed models for generators, HVDC, and facts. All your faults have to be in there and everything. So I'm not going to say much about that except to say that is a whole other, this is kind of, another topic for a different webinar someday. But right now we're just going to focus mostly on the plant model. So that's what the plant's sort of what's in there. When you decide you need to, follow the, say, NERC recommendations or IEEE and say, okay, we may do studies in the future. What do we need to do next? Well, your first step is to create requirements, right? You need to say what you want. What are you going to require from generators who are connecting into your system? What do they look like? Well, they range. They can be quite simple and be essentially a framework, or you can use checklists, which give kind of a more rigorous set of points to check that the people submitting the models will know that you're looking at, or you may actually supply detailed test bench models. But in common, they will have requirements for accuracy. So the model needs to be sufficiently detailed. We need to have the model, the PLL. We need to have the intercurrent control loops. All of those things have to be in there, and they have to be correct. They're not a generic PLL. We don't want to put somebody's idea of a PLL. We want the actual PLL to be in there, and we want the actual protection algorithms. We want it to be usable, right? So the model has to have some functionality in it that allows it to operate in a system context. And usually that has to do partly with the specific tool that you're using. Is it, a certain minimum simulation time step, for example, so that the model runs quickly enough? Or is it, various features of the simulation tool? Or is it a requirement that the model needs to be working together with another model? So they both, run in the same case. So it has to be usable. It also has to have, hooks so that you can control it, right? So it can be accurate, but if you can't control it, then there's no use in a study. It needs to be site specific. So does it represent the actual equipment being used? So this is really important too, because if you've got a really accurate model that's really usable, but it's for the wrong inverter, or it's parameterized wrong, it's configured differently than what will be on site, then it's also useless to you. And finally, we like to have some requirements for performance. So the model should be able to at least basically perform the way you need it to in your system. So, does it ride through a fault? Does it, change its voltage when you give it a different voltage reference, et cetera? So that's not to say, if it gives you basic performance, it's fine. It just means that it's probably okay to start using in a full study where you'll finally determine, let's say, acceptable performance. So I put down here a smattering of example requirements. And I think the message here is that if you're new to this, there's a lot of material now, even in the last few years, very, very good material, people who have tried this before. So I've already referenced, IEEE 2800 has some details in there. We have our own standard that you're free to, copy and change and do whatever you like with or look at. AMO in Australia, I would say, have probably one of the most extensive sets of requirements and tests that they want generator proponents to go through. ISO New England has been doing this for a long time, and they've very recently updated their PP5-6 requirements. ERCOT is also quite experienced in this area. They've gone through a number of revisions of their requirements and their test protocols, and there's actually many others now. Hawaiian Electric, SPP, CAISO, Alberta Electric, System Operator, TVA, and many others actually all have requirements, and lots of folks are looking at this and developing them. So there's a depth of research of resources here that you can lean on to help develop these. I wanted to quickly touch on who should check the models. So once you get the models coming in, at what point are these models checked for quality and usability, accuracy, usability, site specific, et cetera? And you know, it's a good question, and various people do it differently, but my opinion is that the more checking, the better. The checking is the quick part, okay? The studies are the long part. So if you're getting really good quality, well-checked models all along the way, in the end, things go smoother, and that's our experience for sure. So OEMs need to provide, you know, very good unit-level models, validate them, use the best practice on creating them. The generator owners or the geo consultants generally are packaging these up. They're putting the models together and preparing them. They need to do these checks. They need to know what the interconnecting utility is going to look for, what kind of quality needs to be in there. You need to check them before submitting. And the TOs should probably also check, because before you're going to do a long, expensive study, potentially with many different models in it, you don't want to go in with models that aren't going to be useful. So spend just a short time on how. Now, I'm going to lean on a couple of you know, folks here. I'm basically always leaning on everybody else, but here's an example from ATC, is a utility in the MISO footprint. Recently produced this. Can't quite read the date. It's like March or something. Not long ago. And this is, I think Damien Sommer is one of the, I'll throw him under the bus, say, sort of drove this in a lot of ways, and had some help from Lucas Unruh in our shop as well. So I'm gonna lean on some of their stuff here. But I'll give you an example of how you would take a requirement and sort of push it through your, or bring it into your system library. So you start with providing requirements, like I said, accuracy, usability, et cetera. And these are done at the moment by MISO. So ATC can just lean on MISO, who have, you know, a set of requirements for accuracy. So these aren't things you can always say, you can't always check all of these things, but you can provide a requirement that they exist. So it would be, you know, full detailed inner control loops of the power electronics, represent all control features pertinent to the study, represent the plant level control, et cetera, right? So you have the requirements are published, they're out there for people to refer to. Sorry, I'm back a slide now. Two screens here, that's what's messing me up. Right, so this is the MISO's business practice manual that they can refer to. Then in the case of ATC, they provide a series of Excel spreadsheets for the geo to fill out. And I think one of the, you know, this can be done after the fact. You can provide these spreadsheets, and then you can say, you know, have the, and this is I think what ATC did for a number of years, is just provide the requirements, and then the models would be submitted, and ATC would check them, and then throw them back if they didn't like them. So this is the starting place, as you provide these checklists. Usability things, right? And since they're using PSCAD, then they'll ask for some specific things, but they want, you know, some documentation about which model is being submitted. They want documentation on how to run it. They want simulation time step requirements, Intel Fortran requirements, PSCAD versions, snapshots, multiple runs, all kinds of things just about usability, right? And the interconnection customer can, if they don't like it, they can say, you know, not applicable, or they can say something about that, and ATC can say, what do you mean not applicable? And you can have this kind of discussion if you need to about various requirements. Another spreadsheet that checks the site-specific nature of the interconnection, right? So you have You have a generator, you have single line diagrams, you have specific machine MVAs, inverter voltages, generator step-up transformer, winding kV and configuration, transformer MVA, all of these things, they should match in the PSSE model, they should match in the MISO DPP application, and they should match in the plant model. So you can go across here and these numbers should all be the same, right? And finally, you can do some performance checks. So this is a fairly short list, fairly simple test, and they've got a document that prescribes what the pass-fail criteria is for these. But you do a flat run test, phase to ground fault, 3-line to ground fault, 100%, 3-line to ground fault at low power, 3-line to ground fault. But if there's a battery that's in the plant and it's charging, you can look at that. They do a system strength check over frequency, voltage step, over voltage, under voltage, etc. And then they do an extra test. So this is for NERC within the PRC24. In that region, they want you to not trip in their enter momentary cessation. So this is all their specific requirements for their system, what they want. And you can say, yeah, I did good, I did good, I did good. Had a little trouble here. I, couldn't go less than 2.5. And ATC can say, well, that's okay. 4 is all I needed, or something like that, right? So this gives a bit of back and forth about the tests. And then now they go a step further. And instead of saying, this is what we want you to do, we actually want you to test it yourself before you give it to us. And I think this is a little bit out of frustration from the number of iterations that were happening with models that were being submitted, not really meeting the criteria. ATC would check them and have to throw them back. The model would be submitted again, not really meeting the criteria. It would be, tested and thrown back. It was wasting a lot of time for ATC. And so they said, well, why don't we just tell you, we'll just give you a test setup. And if you can pass this, then it's a good start, okay? And it's not the first people that have done this. I think ERCOT has still a PCAR tool is a sort of a similar idea. I'm going to quickly demonstrate it. So I'm going to stop sharing for a second. And I'll share a PSCAD window. So the way this works is, this whole file is provided by ATC. All you do as a developer is you basically take this, you take your equipment. So in this case, I'm using a generic power plant controller and a generic solar plant, and the transformer up to the POI. I've got a collector system in here up to the POI, and drop it in here. Okay, you set the power rating, and then the rest of this is an automated test controller. So you can enter a little bit of basic parameters about the plant in here, and then this is all stuff you shouldn't really have to change. All of this stuff just comes with it, and inside the test controller, there's some more guts in here. But the electrical piece of the test controller is the part I want to show you. It's just a source with a variable impedance, a fault with some variability in it, and some measurement. Okay, so you can define the voltage, the frequency, the impedance, and any kind of fault. And then this test controller is now automated. You can go through the list of tests that I showed you in the previous slide and say, I want to look at test number 1 is a flat run test. I can run that, and it will just show the plant running, with no disturbance. So you can make sure it's nice and flat. You can zoom in on the voltages. You can look at the frequency, all of that stuff. Everything should be flat. And then you can go through the different faults, or the different tests. You can say number 2 was a 3-line to ground fault at the POI at 100% power. So now we can watch this thing go through a fault, right? So now we can see how the plant responded to a 3-line to ground fault. And if we want to, we can go back up to the test thing and we say we want to look at fault 5, where we're going to vary the short circuit ratio down to, from 20 down to 2 or something, and keep putting faults on. So we're going to keep weakening the system and adding faults. So we'll see fault number 1, now the system's weaker, fault number 2, system's weaker, fault number 3, system's weaker yet. And we're getting a little shaky now here by the time we get to 2, but it's, it's for information purposes only. You can see how the plant is responding. So they ask the generator owner to go through all of these tests, make a little report, show the results of all these tests. They should basically meet the criteria and then submit the model. Okay, so this is, I'll show you the last, it's kind of nice. You can see in this one, yeah, the short circuit ratio was 20, it was reduced to 5, reduced to 3, reduced to 2.5, reduced to 2. So, you can add more tests if you want. You can add further automation, so it just like cycles through all the tests. And this is, like I said, it's a relatively simple one. You can add many more tests. You can do this to any type of criteria. So even the AMO DMAT criteria, which is hundreds of tests, you can apply this type of automation to it and build this into your model intake infrastructure so that you can save a lot of time. And in fact, it does save a lot of time. So I'll stop sharing this, go back to my presentation. Just a couple more slides here. What should you expect for challenges? Well, a big one's delay. The modeling, adding in EMT is really another type of model that you're having to bring in and check and then finally use. So this loop of getting a model, checking the model, if it's not good, throwing it back, getting another model, checking the model, is it good? No. Receive it again, check it again. That can be very time consuming if you haven't been asking for models or if your criteria are kind of weak. And so that, I put in here maybe 1 to 6 months delay to collect and check all those models. So if you suddenly decide I need to do a study,
Andrew,
this week.
Andrew, sorry, I don't think your screen is sharing properly right now.
Okay, what are you seeing?
Just our title slide.
Oh, really? Hang on a second.
There you go. Perfect.
Okay,
Andrew,
you didn't
are
miss much.
40 minutes.
Thanks, Julia. I'm on my second last slide, so we're okay. So I've got this loop here I was just explaining. Thanks for interrupting me. That's useful. So, you receive the model, check the model. Is it good? No. Receive the model, and you end up with this loop that you end up. And I'm saying that can take a bit of time before you're ready for the study. So if you're needing to do a study right now, it's probably not going to happen if you haven't been collecting these models. There's also some delay, investing in the people and the software to do this kind of work. It takes time to spool this up, and you really need people, right? A lot of your engineers, your planning groups are currently quite busy with the work they already have. Probably going to need some help, and so you need to bring people on. And then once you get into the study, I know we're not talking much about the studies today, but there's another set of loops that can be really challenging. We're going to leave out that the study itself can be challenging, but just the delay aspects. We have the model comes in, now it's been checked, it's good. You do the study. This takes a long time, right? The study is a big deal. If you identify a performance issue, you're going to go back, maybe tune the model and have to repeat the study until it's all good. Once the performance issue is solved, you're moving on. You're ready to, you're ready to put this thing in. If somebody decides they want to change their equipment model, their inverter manufacturer, for example, that may be a material enough change that you'll have to go back right to the beginning, start the model again, check the model, do your study again, check for performance issues. So, this can happen. Just as a reminder, though, like performance issues are a real thing, and these studies tend to identify them. So you want to, that's the reason why we're doing these studies. Okay, almost done here. I'll just leave you with a couple of takeaways, hopefully, from this presentation. So EMT models are a fact of life, right? Like it or not, they're coming. You need to invest in people. You need to get knowledgeable about these things. Start getting your requirements out, your model intake and your checking going. And and collect those models if you haven't already. The EMT models need to be detailed and correct, or the studies become much less useful. So this is to say, going back again, why are we doing these studies? It's because we're trying to add information, right? We're trying to add new knowledge about our system reliability. If we're putting in garbage models, if the EMT models coming in aren't useful or aren't accurate, aren't specific, then you're going to spend a lot of effort and time on a study that isn't adding anything, right? So, the models need to be good, or it's almost like you shouldn't bother doing the studies. Another takeaway, there's lots of examples now of utilities who have done it successfully, and resources available. Once you have these processes and requirements in place, it doesn't have to be, a dismal story of, okay, now we're mired in this, model checking forever. You can do a lot of work to automate this process and streamline the intake, both through software automation, but also by sharing that responsibility between the OEMs, the GOs, and the TOs. The GO can do a good job of checking the model before they ever submit it. So that the TO, by the time they do their check, it's just kind of it's just a check. And the OEM providing good quality models to begin with is really valuable down the road. So I think that's all I will say for now. I'll stop there and open it up for questions.
Great. Thank you, Andrew. A lot of good questions here. So I'll go ahead and get started with that. On the system model, please discuss your experience about the importance of load models and the short circuit contribution in big grid systems.
Yeah, load models are a pain in everyone's neck for system modeling for a couple of reasons. One is many times we don't actually know exactly what they look like. And this is not a new problem for EMT. This is a problem for transient stability for a long time too. We can sort of characterize them, but often by the time you get really interested in exactly what's happening, you find that the data isn't exactly what you need, especially for complex regions. Of course, it can be very important. It's going to be dependent on the system, that you're in. In terms of contribution to short circuit in weak systems, my feeling is it's not so useful that it's actually providing a lot of short circuit current. Some types of loads maybe do. There is, however, a very important impact from load, which is many times with low short circuit ratio studies or weak system, we call them weak system studies or whatever, you end up looking at systems which are essentially generation pockets connected through transmission to strong systems or stronger systems. And the idea of a weak system gets conflated with a conventional transient stability limit or power flow limit, right? So if you push too much power through a line, your voltage will collapse. It's not a weak system per se. It's just physics. You can't push too much power through. So but they get blurry because it's also weakening the system. So you have voltage control problems and so on as you do that. If you put load on the other side of that transfer, it can really help. And so the location of the load can apparently help weak systems, but in some cases it's just offloading flow. I'll also say that load parameters, for example, induction motor load components and so on, of course, do influence power system fault recovery substantially in some places, and it can be a very important factor. The reason I say it's a pain in the neck is because for EMT studies, it slows us down a lot, and we're always looking for speed. So if you don't have to model all the loads, especially all the induction motor loads, you'd prefer not to. So you should think about that question really hard. How important specifically is loads in my study area before you decide whether to model them or not?
Thank you. Next question is, when could we use an average model of the bridge versus ideal switches versus IGBT devices?
Yeah, good question. So the state of the art right now, some of the models that we get have an option. You can use either the full switching models or the average source models. Generally, we don't mind the average source models. You do give up. So if I go back to my now messy picture, really what you're talking about over here is so the average source representation versus the IGBTs, right? So I'll get rid of some of the other noise here. Your average source representation is really what we're talking about there. The question is, if you skip some of the firing controls, so the comparators and the final firing to IGBTs and replace that with essentially take these, there we go, take these VABC values and just create a voltage source that is sort of smooth, but the right magnitude and phase. You're still keeping this guy in the loop. This PLL is really important. You keep that in the loop with the average source representation. You still have your intercurrent control loops, and you still have, for the most part, your protections, right? So what you're missing tends to be just the firing of the IGBTs, which makes that signal noisy. So you miss any potential harmonic issues that you might excite in the controls with the switching frequencies, with any specific switching dynamics, which granted can be an issue, and you can see ride-through issues occasionally with that sort of thing, but it's not likely. And most of the time, in order to get a model that can properly represent that harmonic, those harmonic interactions that are being impacted by the firing controls, you will also need to create a lot more detail in your plant model and maybe your system model. So, you know, by adding this switching noise into the system, you might get this artificial feeling that, well, I've added this now, I can see harmonic stuff now. It's not even really true. So it runs a lot faster with the average source representation, and you don't give up much by leaving out that IGBT switching. So generally, you know, it's okay to use average source representation for most of the dynamic performance studies that we do.
Thank you. Next question is for me. Is there any area already actively validating IBR EMT models based on actual events in operations?
Yeah, good question. We need more of this. And I think in the last few years, people have started to put in a lot more DFRs, and we're starting to see a lot more of this. I would highlight a couple of areas where, and I'm sure there's lots of people doing this, but I know that Hawaiian Electric folks have put in a lot of DFRs, and they have a lot of IBRs, and now they're starting, and they have a lot of detailed PSCAD models too. So they're doing some of this work now. First results coming in are not super good. Comparisons are not very good. Some of that is older units that have been tripping, and the comparison with the older PSCAD models is not very good. I think ISO New England has also been doing some of this as well, maybe others.
All right, thank you. Next question is, should we include power plant controller functionality in the EMT model? Is it always required?
So that's an interesting question. Now we're asking for power plant controllers and detailed power plant controllers all the time, okay? But that's relatively recent, and there's a reason for that. In the past, these power plant controllers have been very simple and relatively slow, okay? So they're acting really slowly, and they're not really moving the reference powers very much in the time frame of a PSCAD study or an EMT study. So in the past, we kind of glossed over this and said this is not that important. Then we started to see system events that were happening, especially plants oscillating against other plants. And this was actually being identified by operating groups, relatively slow oscillations that were having to do with power plant controllers. And these were, significant events. Part of the issue was, I don't know if I have another picture here. Yeah, here. The communication between the power plant controller and the inverters wasn't modeled right. It was, there were delays in there. But so that's one reason why we started to model them every time. There's also another effect that can happen where the plant goes into a ride through and comes back out. How the PPC reacts during that period and comes back out of it, and the inverter transfers its control back to the PPC can be interesting. It can create issues, cycling in and out of those modes and so on. But the real reason we're really starting to push on this now is that these PPCs, it used to be, you would say the inverter control did all of the fast stuff, the PPC did all of the slow stuff. If there's a fault, PPC just put its hands over its ears. This is no longer true. These communication links are becoming very fast. In some cases, they're pushing them faster and faster, much less than a second, and integrating some of the functions that we initially would have attributed to the inverter are being taken up by the PPC. So the PPC models, if you ask for a real code model from some of these OEMs, are extremely complex. There are many parameters, many communication dependencies between them and the inverter. So sometimes they're still simple and slow, but now it's not a given anymore. And so PPC should definitely be considered in a plant model now, at least considered.
All right, thank you. Next question is there a control bandwidth threshold approximately beyond which we cannot use phasor domain tools anymore and must use EMT?
I understand the question. I'm not, I don't know that I would like to frame it that way exactly. A simple answer would be to just say that you could look at the simulation time steps, right? And say, well, if your phasor domain tool is operating at, say, 1 millisecond, then you're not going to be able to represent very fast controllers and fast effects, because of that. But it's not necessarily true that an EMT model can represent everything much faster. It's going to depend a little bit on what you've included in your EMT model, in the controls, and also in the system model. Likewise, the phasor domain model can add in features that may be useful, but even at a longer bandwidth, longer than 1 millisecond, then it's still an RMS-based tool. At least many of the commercial tools that we use are. So something like SSR, you can't look at it, right? So there are resources out there that sort of give you that kind of bandwidth picture, and you can probably look them up. But yeah, maybe I'll leave it at that.
All right, so I'll take one last question, even though we're on at the top of the hour. I pair up two questions actually. So great stuff about modeling, but how can TO be sure that actual development will behave the same way a submitted model did.
Yeah.
And then the other kind of related question is, how do you test large signal performance prior to operation?
Great questions, and really the topic for another, it's another whole talk, at least one. I would encourage you to look at some of the work that is currently being done by the drafting groups in IEEE 2800.2. Those are very hard questions. And I know Julia is the subgroup chair on the commissioning validation, basically the validation work, and that question of validation goes right back through to the unit level validation. How do you validate? So in short, you need to validate the unit level model against tests, whether it's RTDS tests or hardware in the loop tests or actual test bench tests. And then you need to use those validated models to create plant models like what we talked about, put them in your studies, do your studies, get into the field, do what you can in the field. You need to do what you can to also check back with your parameters to the models. And that turns out to be a huge gap. Once these things are going into the field and somebody actually checks what the parameters are, they no longer match what was put in originally in the models and what was studied. So that needs to be checked, and we're really bad at that right now. Not me specifically, but I think as an industry, we're really bad at that. But in the end of the day, you're going to be leaning on these models to check the large signal performance until you get enough maybe DFR data to sort of spot check it. But if you're going to be doing large signal testing, you're going to have to lean on your models. I mean, I'm a big proponent of putting 3-line anti-ground faults on primaries of transformers for science. So I'd be happy to do more of that.
All right.
Nobody agrees with me on that.
On that note, we are over top of the hour, so I'll go ahead and wrap up. I want to thank Andrew once again for this really informative presentation and the audience for your attention and great questions. As I mentioned earlier, an email will go out once the video has been processed and posted, and we'll answer all the questions that remain offline, and that will be posted as well. As I mentioned in the beginning, we would like to invite you to our Meteorology and Market Design for Grid Services workshop, as well as long-term load forecasting workshop, which will be held on June 13th through 15th in Denver, Colorado. The next ESIG webinar on assessing the value of grid-enhancing technologies, modeling, analysis, and business justification will be held on June 1st. And will feature Jake Gentle from Idaho National Laboratory, Sean Morash from Telus Energy, and Ken Donahue, who is ESIG Grid Enhancing Technologies User Group Chair. Further information on all of our webinars and meetings can be found on our website at www.esig.energy under events, and our newsletters and information emails, and you are all invited to attend. Andrew, thank you once again for this very timely, informative webinar, and thank you all for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone take care, stay safe, and thank you for your participation. See you soon.